So the central concept of calculus is the concept of a limit. And a limit is an answer to the question, how is my function behaving, not at a single point. So it's not about plugging in a value into your function and getting an output value out of it, but it's about asking and answering the question, what is happening to the value of this function near a certain input value, not at that value, but close by. And not just a little bit close by, but arbitrarily close by. The closer that I get to a certain point, the closer that my output values get to a certain value. And so this activity is going to ask you to wrestle with some of those questions, the first of which I want to talk through together, and then I'll get you into your groups and doing this collectively. So on this graph, so this is the graph of some nasty looking function, right? It's got this weird looking behavior that happens near the point x equals 1, right? If I were to evaluate the value of this function at x equals 1, the value that it would spit out would be the y-coordinate of this point on the graph, which lies directly above y equals 1, right? So f of 1 is going to be that point on the graph which lies above the x value of 1. But the limit is an answer to the question, how is this function behaving not at x equals 1, not right here above the point 1 on the x-axis, but very close by. So as we approach x equals 1 from the left side, what are my y values doing? As I approach the value x equals 1 from the right side, what are my y values doing? And so the answers to those questions can in principle be very different from one another. And the first example that we see here, as my x values are approaching 1, as I approach x equals 1 from the left, the y values, as I approach that point, so the y values of this black dot, right, that are sort of approaching this point from the left, those y values are approaching the value, and it looks like 1, a little bit more than 1, it's going towards 2. It looks like the y values are approaching 2, as my x values are approaching 1. From the left-hand side. So as I get closer to 1 on the x-axis on this graph, I'm getting closer to 2 on the y-axis on this graph. So if I were to answer the question, what y value is the dot getting closer to as x approaches 1 from the left side, I would say that that value is 2. Right? So that's going to be the beginning of the discussion about limits. So what we would say in this example is that the left-handed limit of this function as x approaches 1 from the left-hand side, that left-handed limit has a y value of 2. And so this first activity is getting us to think and talk in those terms about limits and about approaching x values from either the left side or the right side and looking at what are the y values doing as we approach those given x values. You're being asked to wrestle with the definition of what a limit is in calculus. It's a way to say what story is a function telling us, not at a single point, but near that point. And so the examples you worked through here were ones in which the story of what that graph was doing just barely to the left of a certain x value, and the story the graph was telling just barely to the right of that same x value could be different from one another and also different from the story that that graph was telling right at that x value. So in the first set of examples you worked with, we had this graph where the limit as we approach x equals 1 coming from the left side had a y value of 2. The limit as x approaches 1 coming from the right side, so moving from right to left as we approach x equals 1, has a y value of 3. But the filled in circle on the graph tells me that f of 1, so the story being told at the point x equals 1, is different still than those two. It looks like it's about 1/2 or something like that. So those are the 3 different stories that a graph can tell about a point in its domain. What's going on at the point that we get just by plugging that point in and evaluating f of 1. And then the 2 limit stories. What y value are we approaching as we come towards that point from the left? And what y value are we approaching as we come in towards that point from the right? And those 3 stories can in principle all be different. But when all 3 of them are the same, that's the best of all possible worlds, because then we don't have to worry about whether we're approaching the point or whether we're at the point. And we don't have to worry about whether we're approaching from the left or approaching from the right. When all 3 of those stories agree with one another, we say that our function is continuous at that point. And so on this last example, we started out with a function that was not continuous at x equals 3. And asked the question, how could we make this function, how could we change this function so as to make it continuous at x equals 3? And in this example, what you noticed was that the story that the function was telling us at x equals 3, the filled in circle here, the y value was 2. The limit as we approach from the right of this function towards x equals 3 was telling me the story, yeah, the limit from the right is also equal to 2, but the limit from the left was telling a different story. The limit as we approach from left to right towards x equals 3 gave me a y value of -1. And so to repair that, to bring all three of those stories into agreement with one another and make this function continuous, we would have had to do sort of one of the things that your groups ended up figuring out how to do. Either move this point at x equals 3 down so that it matches up. So instead of having these disconnected pieces to the graph, now the graph actually joins up there so that the right-hand limit, the left-hand limit, and the value at that point are all the same as one another. So we could do that by moving just that point on the left, or if we wanted to, we could move both of those points. But the point is to no longer have a jump happening at that point in the graph. Sometimes in calculus we say that a continuous function is one whose graph that you can draw without having to lift your pencil off the paper, right? And I can draw this shape without having to lift my pencil off the paper, but I could not have drawn this shape unless I lifted my pencil off the page at this point and moved it from here up to here. Right? So to make this function continuous, I need to make it so there's no more jumps in the graph. Right? So graphically speaking, that's what continuous functions end up looking like. So to wrap up our introduction to limits, I want to talk about how limits work when it comes to formulas. So how would we do this process if instead of just using a graph to do our reasoning, what if we had to do it with formula? Okay, so that's what this example is going to help us to figure out. So a typical limit question, at its basic essence is just you give me some function defined by an algebraic formula. So here's a function defined by a formula, x squared plus x minus 12 over x minus 3. And then ask me a question like, well, what is the limit of this function as x approaches a given number? Okay. And so in our example here, the number that the x value we're trying to approach is the x value 3. So how would we do this? So as in any sort of calculus type problem, I want us to be able to think about it flexibly from all these different perspectives. From the algebraic perspective, yes, but I also want us to be able to think about it graphically, which you just did in this first activity, and also think about it numerically from a data table perspective. So this data table that's right behind me here in the frame. So let's think about it in all four of those different ways, but the algebraic way is going to be, I think, the new one in contrast to the activity that we just did. So let's take these one at a time. If I were to ask, a graphing calculator or something to give me a graph of this function that has this formula, it would do that, and it would give me a graph that looks like, I'm going to show it on the screen here in just a moment as soon as I get this all set up right. Here we go. So here is a graph of this particular function. And what you notice, what I notice at least, is that the graph looks like it's just a straight line. But something weird is happening on this straight line that should give us a little bit of a reason to pause and think that there's something interesting going on. I got to move my frame just a little bit again here. Namely, we notice that as x approaches 3, the x value that we're actually interested in this limit problem, it looks like something's happening in this graph right here. There is a little teeny tiny point missing, and that's what that little open circle means. Anytime you see an open circle either on a graph or on a number line for an inequality, that open circle means there's not actually anything here. There's a little gap, right? So something funny is happening here at this point on the graph. But at least this sort of gives me some initial reassurance that there's some stories in this graph that are being told in a sort of a nice way. And what I mean by that is the following. I'm going to go back to my whiteboard here. So here's a picture of my graph. Based on the activity that we just did, we can say the following. It sure seems like that this function has a limit as x approaches 3 from the left-hand side. And it looks like this function has a limit as x approaches 3 from the right-hand side. Respectively, those are going to be the stories that are told by this portion of the graph coming in on the right-hand side, right? It's going to tell me about the limit as x approaches 3 from the right. And conversely, the limit as x approaches 3 from the left is going to be a story that's told by the portion of the graph on the left-hand side of 3. But on the other hand, we have this part of the story that's told at the point x equals 3. So at x equals 3. But that would be the value of my function, which is directly above x equals 3 on the x-axis. And because there's an open circle there actually is no story being told by f of 3. f of 3 on this graph is actually undefined. There's no filled-in circle there. There's no point on this graph that lies either above or below the point x equals 3 on the x-axis. So f of 3 in this example is undefined. We could have known that from the algebra as well. If I just tried to evaluate what is f of 3, if I plug 3 into this expression, what I'm going to get is 3 squared plus 3 minus 12 divided by 3 minus 3. 3 squared is 9. 9 plus 3 minus 12 is 0. And meanwhile, downstairs, 3 minus 3, that's also 0. But that's a problem, right? Because in any division problem, I cannot divide by 0 and get a number that makes any sense, right? So that 0 in the denominator should be a big red flag. It's a big clue to the fact that something has gone wrong here. All right, so this 0 in the denominator is why we know that f of 3 is undefined from an algebraic perspective. All right. And the graph shows that by the fact that there is no point on my graph, either above or below x equals 3. So just plugging in 3 into my function is not telling me any story at all. But notice, when I ask you what is the limit is not asking for what's happening at that point. It's asking what's happening nearby that point. What are we approaching, not what are we at that point. So we can still do this limit problem even though the value of the function is undefined. Let's think about how to investigate this question numerically. So according to what's behind my head here, if we were to try to use a data table to make this thing happen, I'm going to move myself out of the way here real quickly. Oh, having trouble grabbing my face on the screen. So we can investigate this question using a table of data to investigate what's happening nearby x equals 3. Now that we know that there is no value for f of 3 is undefined. So I'm just going to write in this data table, undefined, underneath x equals 3. But if I want to know what's happening nearby x equals 3, I should choose some values that are close, but not exactly equal to 3. For example, if I choose 3.1, that's going to tell me something about what's happening to my y values nearby to x equals 3. So let me set myself up for doing that here. F of a, I'm going to add this in here. We're going to edit, make my steps 0.01 and go from here to here. Sorry, I'm just getting this set up for us so we can see what's going on. All right. So I'm just going to use my graphical tool to do this. So at the end of the day, both our left-handed limit is approaching a y value of 7 as x approaches 3, and also our right-handed limit is approaching 7 as we approach x equals 3. And so in this example, just based on the numerical exploration, we expect that the value of this limit, and if we don't specify whether this limit is left-handed or right-handed, I haven't done that here, I've just said x approaches 3, so this is what's called a two-sided limit. Two-sided. The two-sided limit means what value does it have if we're approaching from the left and right when those values agree. And in this case, those values do agree with one another, and so that's how we're able to call the two-sided limit 7. Limit as x approaches 3 of f of x is 7. But okay, we still haven't answered the question, how would we do this using algebra? We investigated it using a graph. We investigated it using a set of data points where the x values got closer and closer to 3. But now, how do we do this without those? How do we know for sure from the algebra that the value of this limit should be equal to 7? I'm going to put my equal 7 down here at the bottom. Well, here's the trick. The trick is that I want to rewrite my expression here by simplifying it to the extent that I can. And I can simplify this expression if I notice that the numerator in x squared plus x minus 12 can actually be factored. And this is where some of those preliminary algebra skills start to come in handy. My denominator is still x minus 3, but if I'm factoring my numerator, I'm looking for a pair of numbers which when I add them together give me positive 1, and when I multiply them together give me negative 12. It's the old sum and product factoring trick for quadratic trinomials. And that pair of numbers is negative 3 and positive 4. If I add those together, I get positive 1. If I multiply them together, I get negative 12. Right. So my numerator factors is x minus 3 times x plus 4. But the reason that factoring actually helps us is that now we notice that the numerator and the denominator of this rational expression have a common factor of x minus 3. And because they have a common factor of x minus 3, we can cancel that common factor, leaving only x plus 4 on the top and an empty factor of 1 on the bottom. So that simplification, what that simplification actually accomplishes from a graphical perspective is that when I cancel that x minus 3 out of the denominator, no longer will that denominator become 0 if I were to plug in a 3 into it, right? And so that means that my new function actually is no longer undefined at x equals 3. My new function would actually fill in this hole in the graph that previously existed where x was equal to 3. My new function is just the function f of x equals x plus 4. And if I graph the function f of x equals x plus 4, what I get is just a straight line without that missing point here anymore. And I can evaluate that straight line when x is equal to 3 just by plugging a 3 into the expression x plus 4 for x. And 3 plus 4 is equal to 7. So that's where my 7 came from. 3 plus 4 equals 7. So notice what the overall arc of this was. We started with an expression which was undefined at x equals 3 because this denominator was becoming 0 when I try to plug in a 3. And so f of 3 didn't exist. But when I simplified this expression in a way that resolved that problem in the denominator by canceling this common factor of x minus 3, now I get a function that is defined at x equals 3 and which is otherwise identical to my original function everywhere else. So the limit remains the same after I do that cancellation. The only thing that's different is that my new function is continuous at x equals 3. And so the story that it tells at x equals 3 is a real story, whereas my original function did not tell any story at x equals 3. And because it's continuous, the story it tells at x equals 3 is the same as the story it tells near x equals 3, which is the limit. So factor if you can, simplify to resolve the problem that previously existed, and then, and only then, can we plug in a value for x that's going to give me the story at my point, which now that my function has been made to be continuous is the same as the story near the point, which is the question that's being asked when we asked for the limit.